Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from A3Cube. Once again, we have Emilio Billi. Emilio, welcome to the show.
Thank you. Thank you very much. It's a pleasure to me.
Yeah. Well, thanks for coming back on. I wanted to ask you about, what's new with the company, and I understand you have some new product news for us.
Wonderful. We are growing. So after we launch our fabric technology, now we develop a software foundation that permits to use our fabric to create a complete solution into scale-out and also converged solution where intensive I/O are required. So we can express all the power of our fabric in a very easy-to-use complete product.
Well, terrific. Well, I brought your slides up. Why don't we do that, and then we'll do a Q&A at the end.
Okay, I try to explain it the best way as possible. So, starting from the slide 2, the idea was very simple that came in our mind. So, if you look at the industry in the latest past 5 years, you see that the focus of storage architect was to speed up the communication between the CPU and the storage. And many companies create new kind of storage devices that can really improve these. For example, we are assisting the introduction of massive SSD solution, but also PCI Express SD, now NVMe, PCI Express SD solution, and also in-memory storage solution. If you look at this solution, they are really very good. If you see the benchmark, they speed up the application many times, especially databases or in any case virtualization, and we can say applications that require very fast access to the data. But looking deeper into this solution, you find that are all local solutions. So what does it mean? It means that this solution fit inside a single server and provide local acceleration. What about when you want to scale? This is the problem that we had in mind when we start to create the foundation and our fabric, and why we need to scale out. So, jumping to slide 3, I try to create a focus of the situation today. If you think of the situation today about especially analytics and how the world is evolving, you see that we have to fight with the data information that are coming from 1,000 different sources need to be analyzed. And it's different from the past, because in the past we had SQL databases that use structured data, so tables and so on. So most of the SQL databases were designed to fit in a single machine. It was really easy to analyze the data because you have the data already organized and so on. So local acceleration for traditional SQL database is more than enough, so it's perfect. But what about this new kind of data? New kind of data require a new kind of approach. In fact, software industry create a new kind of database, like NoSQL, not only SQL database, but also entire and complete platform to analyze the data. Like, for example, the most famous is Hadoop. We have a Storm, we have other platforms that are coming to the market. Okay, all these platforms have one thing in common, so are not anymore related to a single server. So, in one word, it's impossible to install Hadoop in a single server. So all these solutions are designed to be clustered. So they are not anymore a standard data center application, but are more like to high-performance computing type of application where the parallelism of the application is very important. In fact, we can call these a massively parallel application. And so they require a specific hardware that can fit these parallel needs. And this is a game-changing because everything is changing. So if you look to the solution that today we have to analyze, to provide access from this application to the data, are all traditional, so are not good when you try to scale. In fact, if you go to the slide 4, I put some of the constraints in scalability. So local acceleration, fantastic. We can scale quite linearly with the new technology. We can improve 10x or more the access to the data. But when you try to scale out in a cluster solution, something go wrong. So your performance became flat, and more or less the degradation happens very soon. Why? Because all these scale-out applications are designed at least with some big bottleneck inside the architecture itself. The most important is that all these require a metadata synchronization that normally is a single server that provides the positioning of all the files when you try to scale out in multiple nodes. What does this mean? If you have an application like Hadoop or like any parallel application that requires to access to a data, before to access directly to the data, because we don't know where the data is, we need to contact the metadata server. The metadata server had to say to the application where the data is stored, and then we can directly access to the data into the storage. Imagine when 1,000 of single processing try to do the same. So this single metadata became very soon oversubscripted, and the performance became very slow, especially when you try to scale a large number of nodes or large capacity, and the number of applications that would like to access to these storage, global shared clustered storage became very high. The performance doesn't scale. Another stuff is the throughput, because normally in traditional scale-out storage, we have a finite number of filer or controller that are connected to the client. So what does it mean? That you scale in capacity because you can attach hundreds of disks to this filer, but the number of I/O interfaces that you can use to connect these disks to the client where the application is running is normally limited to the number of the filer, 2, 3, 4, nothing more. So then all these disks are connected with the fiber channel. All these fiber channel is shared together, all the disks, and the bandwidth of the fiber channel is very low compared to the emerging technology in PCI Express and so on. So at the end of the story, everything appears as a bottleneck, so you can scale very easily in capacity, but you can scale in performance. And high-performance computing and high-performance data analytics require to scale also in throughput to access concurrently to the data from each parallel process. So we need to change something. The architecture needs to change. So we find a solution, if you go to the slide 5, that can appear very easy to understand and also very powerful, and this thanks to our fabric. So we create a directly access from each single scale-out server or storage controller or storage server to the resources of the remote one directly, using directly memory-to-memory access. So it means that, for example, the node 1 can access to the resources of the node 3 in terms of SSD directly, using an extremely low latency fabric that is an extension of the PCI Express. Not only, we can do something that is also unique, because thanks to our extremely low latency fabric, we can also access from the CPU 1 to the memory that belongs to the server number 3 directly. So at the end of the story, through our software foundation, we can scale out in storage, aggregating the SSD or the disk all together in a global file system, and also aggregate the memory to create a scale-out caching in-memory file system that grow with the growing of the capacity and provide reading and writing caching directly into the DRAM. So the application now can extol the power and the latency of the directly memory access to a reading and writing growing elastic caching. Another stuff that is really important to mention that this architecture permits to avoid completely the use of the metadata synchronization. Thanks to this very powerful fabric, we can distribute the metadata tables across all the nodes and using an hardware mechanism that is built into the fabric to synchronize the metadata automatically. So when a file is changed, the fabric automatically, using a multicast, broadcast, and other mechanisms, synchronize all the metadata across the node, creating a global common index of the position of the file. So when I access to a single server and I would like to access to a data, the hardware provides the right positioning of the data and take the file directly. So you don't have anymore the metadata synchronization. This also avoids the use of the one server that is a single point of failure, because if in case of scale-out storage the metadata fail, you can lose the access to the filer. So in this case, we solve two problems with one single stuff. Then we can scale linearly in throughput, because now when you add a server, you add I/O capacity to the data center. We have direct I/O remote access with extremely low latency, so we can extol the power of the modern technology like in-memory channel of NVMe Express. And everything is designed to support completely unmodified any kind of storage and memory device. The result, if you go to the slide 6, is quite visually to understand. So instead to have a bottleneck in scalability due to the incapacity to scale in throughput from the standard scale-out architecture, we have a virtual point-to-point communication between each storage node or each data and each client. So we have something that can scale in capacity and in throughput in the same way. Application and target application. If you go to the slide 7, I try to resume some of the best applications that fit with the Fortissimo Foundation. The first stuff is that the goal was to eliminate the challenging and costing building system with this application, because these applications are high performance like applications that normally are deployed in standard data centers. So there is no expertise in do that, because high performance computing require a specific knowledge of clustering system, connection, high-end fabric, and so on. And this is the reason because many companies are born to support people to deploy Hadoop and analytics application. We try to create a turnkey solution that is ready to use for this application and is perfect to be deployed in a very easy way. So we target NoSQL applications that are new emerging database, not only SQL, that are in any case parallel application too. We target Hadoop and analytics in general to extol the supercomputing capability of Hadoop into the real world of the data center, and also I/O intense application. Why not? Traditional application like a multimedia application, but also scientific, intense message packaging interface application, and so on, where the access to the data and the extremely low latency of the communication is something that can really take advantages, especially when you work in a convergent environment. So what does this mean? For example, in high performance, we can run message packaging interface directly into the storage node. So in one example, slide 8, we have a NoSQL application that we can easily demonstrate with standard benchmark that using the DRAM caching, this giant scalable DRAM caching that can scale beyond 1 terabyte up to petabyte of the DRAM aggregation, and the extremely low latency communication that permitted to extol really the sharing of the SSD, we can have 1 million of transactions per second with just 5 servers that normally require at least 80 servers. So we, of course, lower the CapEx, the OpEx, and of course, the simplicity is very high because it's less complex to manage 5 servers than 80. The same with Hadoop. With Hadoop, for example, we create a connector that permits to directly use HDFS, that is the file system of Hadoop, inside our storage, eliminating the bottleneck of the name node of Hadoop, that is also a single point of failure, and also introducing snapshot and replication of the data, all hardware-driven, and most important, now the communication between the storage synchronization happens not using the TCP/IP socket like in original Hadoop, but using our directly in-memory communication. Hadoop, by the way, since that is directly connected into this, we can say virtual HDFS, doesn't require any change. So we can use Apache Hadoop or Intel or Cloudera and so on, completely unmodified, and run on top of our architecture, also in a converged mode. Slide 10 for the I/O intense application is quite clear. So it's a turnkey solution for I/O-intense application in terms that it's a completely clustered solution ready to use. So it's something that perfectly fit with the high-performance computing exigence of some of these applications. We can run NPI inside the storage, so we can lower in the latency. For example, we have our NPI is 800 nanosecond of latency for 4 bytes of communication, and of course is fully managed with the in-memory communication. So we have a completely offloading of the CPU because our communication happens at hardware level, so we don't have offload of the computation for perform the communication. So there are a lot of benefits, not only for standard application, but also slide 11 for virtualization. Virtualization can achieve a lot of benefit, especially for the caching of the DRAM. So we can use the global DRAM sharing to caching the read and write operation of the virtual machine across the storage, or in some cases run the hypervisor on top of the storage itself, creating a very disruptive, extremely low latency, bare metal virtualization environment. You can say, how is difficult to deploy this solution to the real world? Well, if you go to the slide 12, I try to explain how it's simple to manage this platform. This platform is designed to be an open platform. What does it mean, open platform? Open platform means that it can fit in any existing hardware server, so we don't use a proprietary or specific hardware. We don't require BIOS changes. We don't require a specific setup, but you can run memory, disk, CPUs. You can choose from all the world the best solution that fit your problem. You can also choose the best I/O interface for the data center fabric. It means 10 gigabit Ethernet, InfiniBand, gigabit Ethernet, whatever. And you just plug into the existing server RONNIE Express network interface controller plus the software foundation. What does happens, slide 13, when you aggregate multiple of these nodes, what you achieve is that you have a global namespace across all the disk, but also unique aggregation of the memory DRAM, that you create a scalable caching system that grow with the capacity of your server, but you have access to the local computation in a scalable way. Behind the scene, you have this super duper fabric that permit extremely bare metal access in terms of latency between local and remote resources, and this permit really to achieve the maximum performance from existing technology and also future one. How to connect these to the existing world? Really simple, I can say. Slide 14. We provide the same interface on all existing storage and computation architecture today. So we support any kind of data center fabric. So you can just connect this cluster machine to the existing data center using the standard 10 gigabit Ethernet or InfiniBand, whatever, and use the standard protocol that you use with the standard storage, network file system, CIFS, FTP, and whatever. So the result is something that is extremely flexible, but at the same time is extremely simple to manage as all existing today technology. One example of the flexibility is given by the slide 15, where I try to demonstrate how is flexible the solution, balancing the throughput and the capacity of the system. For example, if you have a free example. In the first one, case A, imagine you have two controller and 4 disk. You are satisfied with, for example, your capacity, so 4 disk is okay. But you need more throughput. You just, case B, add 2 new server, deploy 2 disk into the new server, you reaggregate the volume. In that case, you have the same capacity of the case A, but you have 4 interface to access to the storage, so it means you double the bandwidth. On the contrary, if you are satisfied with the throughput, so you need just 2 nodes, but you want more capacity, you can add more disk. Everything happens elastically, so is the thin provisioning one of the characteristics of the system. It's very simple to manage too, also in terms of connection to the client that can be also inside the storage, so the client can work virtually in a convergent system or can be external. So the idea is expressed in slide 16, where traditional scale-out storage, this is just an example very well known with a two-filer and disconnected with fiber channel or PCI Express to the filer, where you have to fight with multiple RAID, volume, file system. You can aggregate up to 100 terabyte, but normally you aggregate 16 terabyte per time and so on. And then you map each volume to a single client into the data center. When you want to scale, is a problem because it's complex to manage and so on. With our vision is a global optimization of all resources, where you have all the disks aggregated together, but also the caching or in-memory storage. You have a memory and the storage aggregation that can be managed separately, so you have a maximum flexibility to caching data or to put the data directly into the memory and using the disk to replicate the operation from the DRAM to the SSD. In case of failure of the node, this is really useful because you have a copy of your data with inside the SSD. You can achieve a very easily converged computation, or just you can upgrade very easily adding disk or memory and grow up in capacity and performance. Very easy to use and to manage. The really secret sauce behind this is our hardware interconnection infrastructure that I try to express in the slide 17 very, very fast. So, as you know, in any scale-out storage architecture, you have two networks, the user plane and the data plane. The data plane is normally behind the scene. No one take care about that, but is present. For example, EMC using InfiniBand for his Isilon solution, Ethernet for other solution, NetApp using InfiniBand 2, Ethernet fiber channel, and now EMC with the acquisition of the SSD use also PCIe. All these fabrics are really good, fantastic, high throughput and so on, but for our point of view are two limitations. They doesn't support directly CPU to CPU communication using load and store locally and remotely in the same way. That is very important for our memory aggregation. They are only RDMA, so they support only remote DMA operation. So you don't have directly fully memory access at hardware level between the local and the remote device. What we introduce is a new PCI Express that we call PCI Express with in-memory communication that extend basically the memory capability from the standard RDMA into the global set of memory operations. So RONNIEE Express, that is the name of our fabric, provide unique direct memory access using load and store operation, parallel I/O, DMA, interrupt, peer-to-peer support, all at hardware level. What does this mean? This means that we are not anymore limited to RDMA, but we can just perform the operation into the remote node as we perform the operation in the local one. This enables some very cool stuff that, for example, the most important, we are able to scale linearly with the IOPS, not only with the bandwidth, so we can extol the power, or really the power of the latest SSD technology. We can also scale out in memory capacity up to petabyte because we are not coherent. So we are not limited by the addressing of the CPU. So normally 48 bit, so it means 256 terabyte. We can scale beyond. We don't have kernel involvement in the communication, so it means that we completely offload the latency of the kernel too, so we have extremely low latency, and then we can achieve a scalability that is, of course, higher, at least an order of magnitude of any other solution, thanks to this extremely low latency architecture. Behind the scene, we have also a software solution, software core, that is not just a simple software part, but is the manager of all this infrastructure that take care about the status of the entire ecosystem. In slide 18, I put some of the characteristics. So the software foundation take care about the global namespace, manage the direct I/O in memory caching, create the unique memory aggregations, and provide the managing of multi-level of availability of the system, but also provide the native support for Hadoop and the data reduction and the inline deduplication. These two characteristics are really important because if you want to optimize some operation and you need to optimize the space, you can perform inline deduplication completely in memory, take the advantages from our scalable memory solution that is not anymore limited to the single node, but you can use terabytes of memory, and so you can avoid the latency of the inline deduplication, having a storage that performs extremely fast, but at the same time provide inline deduplication. In the slide 19, I put some of these two characteristics. The first one that I already explained, that is the in-memory deduplication, but also important, the data replication that can be performed in a circular way, most important with the hardware support. So it means that automatically the hardware provides a double copy of your data. For example, if you write a data into the disk 1 of the storage 1, you can have a replication into the disk 3 of the storage 2, and this double copy is provided by the chip of the RONNIE fabric. So no operating system is involved. The value proposition, slide 20, is for our point of view to positioning our solution, Fortissimo Foundation, hardware and software, with the maximum performance that you can achieve installing the existing technology in a scale-out environment that normally no one can do because of the limitation that I explained before, but also in terms of scalability, because you can choose to scale up and scale out in the most perfect way, we can say, required by your application. So you can really tune this solution to extol the maximum performance, or better, the maximum price performance of your application and your specific needs. The idea behind this project, because it's a completely project that will scale with the time, because we are working on next step with the new plugins and so on, is to provide a really disruptive solution that is really borderline between data center application and high performance application in terms of analytics, and also legacy high performance computing application like message passing and so on, with the lowest capex possible, the maximum return of investment because of this feature, but also permitting to add real-time capability to applications that are not born to do that. For example, Hadoop with the directly in-memory caching, reading and writing, or, for example, if you have a legacy MySQL database and you want to perform an in-memory application, you can put your table and your dataset directly into the memory and perform the operation directly in memory without using in-memory specific database, and so on, with an open platform that can be configured in a very and extremely easy way, really taking advantages from the emerging technology that you can find on the market. So this is the reason because we develop all these, starting from the hardware, because it's really true. Who would like to extol the power of his software and to build also the hardware too, to have the full control? And this is what we've done in A3Cube, hardware and software by the same team. Thank you. That's all. So.
Okay. Well, thanks, Emilio. I wanted to ask you about the Fortissimo Foundation. In that, do I have to, rewrite my applications to take advantage of this environment?
Absolutely not.
Yeah.
Absolutely not. All the we have a fully compliant interface, so you can just plug your application using Fortissimo and take immediately advantage from the extremely low latency that we can provide.
Well, terrific. So when we first talked, you brought out the RONNIE Express, right? The PCIe Express interconnect. Then you had the NIC, and now with the software piece of this, do you have the complete puzzle, or are there still pieces that you're going to bring to market later?
No, this is basically all these solutions come to the market as a turnkey solution. So through our system integrators and partners that can work with the end customer to create the best configuration for their needs, and then the system comes as a complete solution where inside you have the fabric, the software, the NIC, all already configured and working in the perfect way to fit the needs of the application target. So it's something that is a turnkey solution where we build all the single pieces, but in any case, this is all part of the same story.
Yeah. And at this point, are you ready to show benchmarks? Because this is a solution, that's for high performance, right?
Absolutely, yes. We are able to show the benchmark, and we are also proud we can say that we have our big customer that make our first purchase order of a big high-performance computing oriented architecture, and we can announce the supercomputing, the coming supercomputer in New Orleans.
Oh, terrific. Okay, so we'll see you at SC14 then.
Yes.
Yeah, absolutely. Great.
Yes.
You going to have a booth there, or are you going to be with partners?
We have a booth, but the solution is in the booth of our customer.
Okay. Okay. Ooh, very exciting. Well, great. Well, Emilio, this is it's great to see this all come together. Is it available today?
Yes, it's available. So we would like to launch to the public the 17th of September. So when we launch, it's completely available on the market. So we are able to start to deliver the solution.
Well, terrific. Well, Emilio Billi, I want to thank you once again for coming on the show today.
Thank you. Thank you to you for your time.
Oh, you bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.